Okay, you have a couple of homework problems this week on Newton's law of cooling, and they're not completely straightforward. So I kind of wanted to go through these with you to make sure that you knew how to do them and didn't come across anything too confusing. So this is how it works. Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings, provided that the difference is not too large. So, if we think of T of T as being the temperature of the object at some time, T, and T sub S as the temperature of the surroundings, then T of T minus T sub S is the difference between the object and its surroundings. Newton's law states that that difference is proportional to that its rate of cooling is proportional to that difference. And so that's what this statement basically means. And we know that that if something grows at a rate proportional to itself, it is exponential in nature. So we're going to view Newton's law of cooling in a way as an exponential function with this adjustment. If we think of A of T, A as the function T of T minus the surrounding temperature, if we let it be that, then we can put it into our regular exponential model. A of T is A sub 0 e to the kt. So we're going to be making this adjustment that A of T is the temperature of the object at time T minus the surroundings. So here are a few examples. This is the first example about a roast turkey, and it goes like this. It says, a roast turkey is taken from the oven when its temperature has reached 185 degrees and is placed on a table in a room where the temperature is 75 degrees. So before they ask us any questions, let's just identify some things that we can see here. The roast turkey is taken out of the oven when its temperature has reached this. This is the temperature of the object, T of T, but it's the initial temperature. It's T of 0 when time is 0. And it's placed on a table in a room where the temperature is 75 degrees. This is T sub S. Okay. So that's a couple of things we need to identify. It says if the temperature of the turkey is 150 degrees, this is another T of T after half an hour. So this is really T of 30 minutes, T of 30 after half an hour, T of 30. What is the temperature after 45 minutes? This is the way I have to figure out, what is T of 45? That's what we have to answer. And then part B, we'll get to that in a second. So the first thing we need to do is get a working model for ourselves. And so the working model is going to be A of T is equal to A sub 0 e to the kt. However, we need to make this adjustment. So A sub 0 right here, let's figure that out. If A of T is T of T minus T surrounding, then A of 0 is going to be T of 0 minus T surrounding. So in this case, A sub 0, or A at time 0, is equal to the temperature when it initially is taken out of the oven, 185 degrees, minus the surrounding temperature of 75 degrees. And so that's 110. So this is what our A sub 0 is that we put into our function. So we have A of T is equal to 110 e to the kt. This is our model. Now they give us a piece of information in part A that can help us solve for K. So it says if the temperature of the turkey is 150 degrees after 30 minutes. So after 30 minutes, it's 150 degrees, but we have to make this adjustment. So what is A of 30? Well, that's equal to T of 30 minus T surrounding. So A of 30 is going to be 150 minus TS is 75, so this is 75. So after 30 minutes, we make the adjusted temperature. 75 is equal to 110 e to the k times 30 minutes. We do our math where we solve for k. We divide both sides by 110. And then we take the natural log of 75 over 110 is the natural log of e to the k times 30. These undo each other. Then we just divide both sides by 30, and we get that k is equal to negative 0.012766. I like to take these out 5 or 6 places. So that's our k. So now we have a working function. A of t is e to the k negative 0.12766 t. All right. So now we can finally answer part A. What is the temperature after 45 minutes? So we just plug in A of 45, and we get e to the negative 0.12766 times 45, and that gives us an answer of 61.93 degrees. However, we have to adjust it back because this is the function temperature, not the actual temperature. How do we figure out T of T? Well, we know we add the surrounding. A of T plus T sub S will give us the actual temperature. So T after 45 minutes is going to equal to A of 45, 61.93 plus TS, 75. So that gives us 136.9 degrees Fahrenheit. That's part A. Part B, when will the turkey have cooled to 100 degrees? All right, we use our function. Where did I put my function? This is our working function, right? When will it have cooled to 100? All right. So we want it to cool to 100, but before we use our formula, we must make the adjustment. What is 100 minus the initial, or 100 minus 75 is 25. This is for part B. Is equal to A sub 0, 1, 10, e to the k, and we know what k is, which is negative 0.12766 t, and we solve using our knowledge of how to solve an exponential equation, and we get that t is 116 minutes is what you should get right there. All right, so the idea is whenever we go to use our model, the temperatures that we put in must be adjusted, and whenever we take a temperature out of our model that we've calculated, we have to adjust it back so that we know what it is in the actual in the actual room. Okay. All right, let's look at number 2. When a cold, so we're going backwards. This was a hot turkey being cooled to the room temperature. Now we have a drink that is cold, taken out of the fridge, being warmed up basically to the room temperature. So it says we got a cold drink, it's taken from the fridge, its temperature is 5 degrees. This is the initial temperature, T sub 0. After 25 minutes in a 20-degree room, this is the surrounding temperature, T sub S. Its temperature has increased to 10. So this says that after 25 minutes, T of 25, the drink is 10 degrees. All right. What is the temperature after 5 degrees? Well, to use our nice formula, we make the adjustment, this adjustment. So A of T is A sub 0, e to the kt. So what was A sub 0? A sub 0 is T sub 0 minus T surrounding. So in this case, A of 0 is 5 degrees Celsius minus 20, negative 15. So this is negative 15 goes right here. E to the kt. Here's our model. Okay, then they gave us this information. They said after 25 minutes, it has increased to 10 degrees. So we know that T of 25 is 10 degrees. So what is A of 25? Is going to be T of 25, 10, minus 20, negative 10. So A of 25 is negative 10, is negative 15, e to the k, and this is after 25 minutes. So we divide both sides by negative 15, we take the natural log, we divide by 25, and we find that K is equal to, just a second, K is equal to negative 0.0162186. All right, now we have our nice little model that we can use to calculate things with. So we know that A of t is negative 15 e to the negative 0.0162186 times t. All right, let's answer part A. What is the temperature of the drink after 50 minutes? Okay, put 50 in for t, A of 50. Put 15 for t, calculate that, and you get that A of 50 is, where did I write that down? I got negative 6.67. Okay, but this is A of t. How do I get t of t? That's what I really want. Well, to calculate t of t, if you go back up here, you just have to add the surrounding temperature to that. So if I take t of 50 is going to be A of 50 plus the surrounding. So it's going to be negative 6.67 plus 20. So the answer to part A is 13.33 degrees Celsius. Okay, when will its temperature be 16 degrees? So we're solving for t. And we want to know when it'll be 16 degrees. But when we go to use our formula, we make the adjustment. So this is t of t. So how do I find A of t? I have to add the surrounding temperature to that. So I want it to be 16, so I have to add A of t plus Ts is t of t. So I want it to be 16. So that's going to be A of t plus, I'm sorry, I have to, sorry, when I put it in my calculator, my function, I'm sorry, when I put it in my function A, I have to take 16 and adjust it by subtracting the surrounding. So I take 16 minus the surrounding 20 gives me negative 4. And then I put it in my little formula here. And I say negative 4 is equal to, right here, my function is right here. There's my nice little function that works all the time. This is where it is equal to negative 15 e to the negative 0.0162186 t, and I use my skills at solving exponential equations. I divide both sides by negative 15. Negative 4 divided by negative 15 gives me a positive, so I can take the natural log of that, and then I divide it by the k, and I get that t is equal to, let me double check my work. I get that t is equal to 81.5 minutes. Okay, so the idea is every time you go to use your exponential model, that's fine, but you have to make that little adjustment with the temperature. Let's do example 3. This one's a little bit different. It says a freshly brewed cup of coffee has a temperature of 95 degrees in a 20-degree room. This is the initial temperature. This is the surrounding temperature. When its temperature is 76 degrees C, it is cooling at a rate of 1 degree per minute. Wait, this rate is a derivative. What they just said is that D temperature with respect to time, the rate of the temperature change with respect to time when the temperature is 76 degrees C is equal to, it's cooling, so it's negative 1 degrees per minute. This is what this information right here said. All right, how do we make sense of that, or how do we figure out what we're supposed to do? They want us to know when does this occur. So we're looking for t. T is what? So right here, dt dt is equal to, right here, dt is equal to the rate of proportionality times the difference, t of t minus t sub s. All right, so -1, the rate of proportionality, is equal to k, which we don't know what that is, but we know it occurs when the temperature is 76 degrees, so it's going to be 76 minus 20. All right, so we take 76 minus 20, and we solve for k. We divide both sides by 76 minus 20, -1 divided by that, and we get that k is negative 0.017857. All right, so now we have k. We can say our working model is going to be a sub 0 e to the negative 0.017857 t. All right, what they want to know is, what is t when this happens? All right, well, this happens when t is 76 degrees. So let's make that adjustment. Do we know the initial temperature? Oh, we do, 95. So we just make the adjustment. A of 0 is t of 0 minus t sub s. So that's going to be 95 minus 20. So a sub 0 is 75. All right. When does this occur? It occurs when t is 76 degrees, but we have to make the adjustment. So a at whatever time this is equal to t of t, which is 76, minus the initial 20. So this is really going to be 56. So we have 56 is equal to 75 e to the negative 0.0178576 t. And we're going to solve for t. Divide both sides by 75. Take the natural log. Divide by this k value. And you'll get that t is equal to 16.34. All right, so that's a few examples of how you can use Newton's law of cooling.